For this lesson video, you're going to want to make sure you have your SI prefixes chart. It looks like this, because you're going to see me pull a bunch of powers and numbers, and those powers are coming from this chart right here. Okay, so make sure you have that when you're watching this video so you'll know what's going on. Alright, so this is our Honors Chemistry Section 3.2 lesson video. And hopefully you just saw what I said and you have your SI prefixes chart out. If not, you can find it on my school website and print one, but it should be in your packet that I've given you already. Alright, so the SI units, or International System of Units, is a revised edition of the metric system, and scientists use it all around the world. So length is in meters, the symbol is M. Mass is kilograms, the symbol is kg. Mass is the only one where the SI unit has a prefix, the kilo on there, so it's not just grams. Temperature is Kelvin, which is represented by a capital K, no degree sign. Time is seconds, which is abbreviated S, not SEC. Amount of substance, this is probably a new one, is the mole, which is abbreviated MOL. We will talk about moles a lot, and we'll celebrate Mole Day, which is October 23rd, just throwing that out there. Next is luminous intensity, that kind of deals with the brightness of something, and the unit is candela, and it is abbreviated CD. And the last one is electric current, which is the ampere, which is abbreviated by a capital A, not amp. So just make sure you know your base units, because I do like to put this chart on quizzes and tests and have you fill it in. All right, so let's move on and talk about those prefixes that I just told you about on that prefix sheet. So prefixes are used to show a very large or very small quantity. For your prefixes sheet, it's important for you to remember the following. One prefix unit equals 10 to the x base unit. I would literally write this on your prefix sheet so that you can use it until you committed it to memory. So I'm going to write it over here just so I can keep referring to it for y'all. So one prefix unit equals 10 to the x base unit. So first of all, what is a base unit and what is a prefix unit? Well, a base unit does not have a prefix. So like meters, liters, grams, seconds, those are all base units. A prefix unit has a prefix. So meter is a base unit, centimeter, millimeter is a prefix. Kilometer is a prefix unit. Liters is a base unit. Milliliters, nanoliters, deciliters, those are prefix units. Grams is a base unit, so kilogram, decagram, megagram, those are all prefix units. So a prefix unit just has one of the prefixes from your SI prefix sheet that you have out, hopefully. Alright, so remember, one prefix unit equals 10 to the x base unit. So we are not actually doing a problem right now. I am just showing you how to use the chart. We'll do plenty of problems in section 3 when you get to that. Good luck. That's like 3 lesson videos long. It's a big section. I love dimensional analysis. Alright, so one prefix unit equals 10 to the x base unit. We're trying to go from centimeters to meters. So I literally follow this. So one prefix unit. So I'm going to write one prefix unit. Well, which one has the prefix? Centimeters or meters? Well, centimeters has a prefix. So 1 centimeter, then I put equals 10 to the x. The x means that can be any number. So this is where you're going to use your SI prefixes chart. Look at your SI prefixes chart and find centi. When you find centi, you're going to see 10 to the negative 2. So that's what I'm going to put in. So I got the negative 2 for my SI prefixes chart. And then base unit. Well, which one's the base unit? Centimeters or meters? Meters is the base unit. Okay, so this is how you use the SI prefixes sheet. Lots of people use it backwards. That's why I spend time going over this. All right, so next we're going to go from grams to kilograms. So again, I'm going to use the same thing. So one prefix unit. So I write one. Which one has a prefix? Grams or kilograms? Kilograms. Okay, y'all, it doesn't matter that kilograms is on this side of the arrow and centimeters was on that side. You still put 1 with your prefix unit. All right, equals 10 to the x. So when you look at your SI prefixes chart, you will see that kilo says 10 to the 3. Base unit, grams is the base unit. Okay, so again, it doesn't matter if you start with your prefix unit and go to base, or if you start with your base unit and go to prefix. You are always going to start with one prefix unit equals 10 to the x base unit. Okay, so maybe pause it, try the other two. So I'll assume you've done that. So we're going seconds to nanoseconds. So one prefix unit. So one, which one has a prefix? Nanosecond equals 10 to the x base unit. So you go to your prefix sheet. It will tell you for nano, it's 10 to the negative 9. And then your base unit, of course, is seconds. All right, so hopefully you got that right. Last one is deciliters to liters. So deci and deca both start with D, but if you'll look at your prefix page, deca is DA, and it's 10 to the 1. Deci is just D, and it's 10 to the negative 1. So just be careful not to get those mixed up. All right, so we start one prefix unit, so 1 deciliter, because that's my prefix unit, equals 10 to the x base unit. So remember, when you look at your prefix chart, make sure you look at D for deci, it's 10 to the negative 1, and then my base unit is liters. So again, we will look in section 3 about how to use these. I'm just introducing how to write them first, and then we'll actually use them in real math problems in section 3. All right, so let's move on and talk some more about SI units. I'll leave this up just in case I need it later. All right, so some units are derived. They're a combination of base units. And so examples include like our SI units for length are meters, but when you do volume, it's meters times meters times meters, so you end up with meters cubed. Or density, we have kilograms and meters cubed, so it ends up being kilograms per meters cubed. It can even go further as to where like a kilogram times a meter per second squared ends up being a newton. Another derived unit is Pascal. You don't need to memorize all these. I'm just showing you that we can combine SI units to make new units, and they're called derived units. So let's talk a little bit about volume. So when you're in lab, there is lots of different glassware and equipment that measures volume. Some of it is more accurate than others. Syringes, burettes, and pipettes deliver liquid with more precision than a graduated cylinder. Now, in our class, we will mainly use graduated cylinders because the labs that I give you, we don't have to be super precise on. However, if you are working in those conditions, syringes, burettes, and pipettes are better than graduated cylinders. Volumetric flasks, like this, are used to contain a specific volume. So when you look at a volumetric flask, instead of having different lines, like a lot of glassware does, there is literally one line. It measures one amount. So as you can imagine, if your job is just to measure one amount, you're going to be pretty accurate. So volumetric flasks are really accurate, but the downfall is they only measure one amount each. And then beakers and Erlenmeyer flasks should not be used to measure volume because they lack precision. That's why in lab, whenever I want you to measure a liquid or something like that, I'll always have a graduated cylinder out, even though you're going to eventually put it into a beaker. A lot of you, you'll just measure right into the beaker. Beakers and Erlenmeyer flasks are not very accurate. We use those as our reaction vessels, not as really a measurement. All right, so mass versus weight. What's the difference? Mass is the amount of matter an object contains, and the SI unit is kilograms. Weight is the force that measures the pull of gravity on a given mass, and the SI unit is newtons. So weight is based on gravity. So if you went to a different planet with different gravity, your weight would change. The mass is how much matter you contain. That is going to stay the same. So since weight is based on gravity, it changes with location. Mass stays constant regardless of location. So here we have a girl. On Earth, she says my weight is 560 newtons. On the moon, it only has about 1/6 the gravity that Earth has. So her weight is only 90 newtons. But since she's the same size in both places, she says my mass is always 56 kilograms. So her mass is not changing. It's just since gravity is changing, her weight changes because weight is based on gravity. All right, next thing we got to talk about, some other things for measurement, is temperature. Temperature is the measure of how hot or cold an object is. Now that's the baby definition. Like that's what they teach you in elementary school. The real definition is in parentheses right here. It is the measure of the average kinetic energy of an object's particles. So it's based on kinetic energy of particles. The more kinetic energy or the faster the particles are moving, the higher the temperature. Heat always flows spontaneously from a substance at a higher temperature to one at a lower temperature. And then there are 3 temperature scales that are used. There's Celsius, Fahrenheit, and Kelvin. Kelvin is our SI unit. Celsius, however, is what we commonly use in lab. Fahrenheit is something we use in America, and it literally makes no sense. I'm not even really sure why we use it. Most people who actually live in America don't even know what temperature water boils at in Fahrenheit, and we're like the only country in the world that even uses it. But we don't even know. It's 212, by the way, if you were sitting there thinking in your mind, ooh, I wonder if I know. You probably didn't, because most people don't know it's 212. So anyway, why we even have it, I don't know. So let's move on and talk about an important temperature scale, and that's Kelvin. So absolute zero is 0 on the Kelvin scale, not Celsius. Kelvin temperature is directly proportional to the kinetic energy or speed of the particles. If the particles are not moving, then the Kelvin temperature is 0. Since particles cannot go slower than stopped, the Kelvin temperature does not have any negative values. So Celsius and Fahrenheit both have negative temperatures, but Kelvin doesn't because it's directly related to the motion of the particles. So once the particles stop and Kelvin hits 0, you can't move any slower. Like even moving backwards is still movement at that point. So absolute 0 just means it cannot get any lower than that on the Kelvin scale. So we have formulas to convert between the temperatures. So between Celsius and Kelvin is very easy. To get from Celsius to Kelvin, you add 273. To go the opposite way, you of course subtract 273. For Celsius and Fahrenheit, though, it's a little bit trickier. So the thing you need to be careful of is your orders of operations. So remember, parentheses happens first. So when you're using this formula to get to Celsius, you're going to do your Fahrenheit minus 32 first, then times your 5 ninths. But when you're using this formula to go from Celsius to Fahrenheit, you're going to multiply your temperature by your 9/5 first, then you're going to add 32. So just make sure you're careful of your orders of operations. All right, so let's look at a couple of these. So it says, if a weather forecaster predicts that the temperature for today will reach 31 degrees Celsius, what is the predicted temperature in Kelvin and in Fahrenheit? Okay, so we have Celsius, we are trying to get to Kelvin. So if you look, our formula is Celsius plus 273 equals Kelvin. All right, so we know Kelvin equals Celsius plus 273. So I would just plug in. So 31 plus 273 equals, and so when you put that into the calculator, of course, you're going to get 304. And your unit is Kelvin. And notice that Kelvin does not have a degree sign like Celsius and Fahrenheit does. All right. So next, we need to change our 31 degrees Celsius to Fahrenheit. So let's go back. So we are going from Celsius to Fahrenheit. So it's 9/5 times Celsius plus 32. That's how we're going to get to, whoops. So it's 9/5 times my Celsius plus 32. That's how I'm going to get to Fahrenheit. So I just plug in. So 9/5 times my 31 plus 32. And so when I plug that into the calculator, I get 87.8 degrees Fahrenheit. Now obviously, because Fahrenheit doesn't make any sense, we will spend very little time ever calculating to Fahrenheit. Most of our time will be spent trying to get away from Fahrenheit because, again, nobody uses it. Why do we use it? I really don't know. Why do we use a lot of things? Like, why do we use feet? That makes no sense either. Other people use meters and centimeters, and that just makes a lot more sense than what we do. But you know what? It's what we do, and I don't see us changing anytime soon. I really wish that we would just switch to the metric system because that would make this chapter a whole lot easier for y'all. All right. So, moving on. So y'all try these real quick and then we'll look at them together. So it says ethylene glycol, the major ingredient in antifreeze, freezes at negative 11.5 degrees Celsius. What is the freezing point in Kelvin and Fahrenheit? And then you can go ahead and try the next one too, but we'll look at that in a second. So I'll assume you have tried this already, and so let's look at it together. So if you look back at your temperature conversions, Kelvin is Celsius plus 273. So I would do negative 11.5 plus 273. And so for part A, I would get 261.5 Kelvin. Remember, no degree sign. Okay, I'm super picky about that. No degree sign. All right, so next we're going to calculate to the temperature scale that makes no sense, and that is Fahrenheit. All right, so if you remember from our previous slide, Fahrenheit is 9/5 times our degrees Celsius plus 32. So we just plug in. So 9/5 times that negative 11.5 plus 32. And so once you solve for that, you should get 11.3 degrees Fahrenheit. All right, so hopefully you got those right. If not, try this one and hopefully you'll get it right before we do it together. All right, so you're going to convert 56 degrees Fahrenheit to Kelvin. So what I want you to notice is I did not give you a formula specifically to get from Fahrenheit to Kelvin. So what you're going to have to do, is convert from Fahrenheit to Celsius first, then Celsius to Kelvin. All right, so I'll assume that you have already taken care of that and you are ready to look at it together with me. So if you look to get to Celsius, it is 5/9 times your Fahrenheit minus 32. Okay, that's our formula to get from Fahrenheit to Celsius. So I'm going to do that first. So 5/9 Fahrenheit, which is 56 minus 32. And so once I plug that in, I get 13.3, but I have only gotten 2 degrees Celsius. Because see, this formula got me 2 degrees Celsius. Sorry. So to get to Kelvin, I need to use one more formula. So remember, we already know what that is. Kelvin is degrees Celsius plus 273. So I would just do 13.3 plus 273. And so once I add that together, I get 286.3 Kelvin. No degree sign. All right, so it's just plugging into formulas. Not a big deal at all. Hopefully you're good at plugging into formulas. If not, get ready. This class is going to be rough. All right. So nothing like some basic plug and chug, as one of my college professors used to say. All right, so moving on to the last thing we need to talk about is energy. So energy is the ability to do work or supply heat. The SI unit of energy is the joule, which is represented by capital J. However, of course, in America, we use calories instead of joules. Surprise, surprise. So our conversion factor to get between them is 1 calorie equals 4.184 joules. So surprising fact, my dad went to Switzerland one time for a business trip, and he brought some chocolates back for me. And so I looked just to see, like, there's no way they actually have joules listed in their nutrition facts, and they really did. I was just like, oh my gosh, this is the best thing ever. I wish I saved the box now. But I was just so baffled. I just thought for sure they still would use calories. But nope, they had joules on there. So good job, Switzerland, for making more sense than America does. All right, so number 5, if it's just a verbal answer, I'm just going to say it to save time. I know these videos are long. I'm sitting here making them. So if you're just watching it, it's much longer feeling to actually make the videos. So it says, what are SI units for 5 common base units used in chemistry? So notice our chart actually had 7, but the first 5 are the 5 that we'll use in this class. So we're not going to use the candela or the ampere. So our 5 common base units are meters, kilograms, seconds, moles, and Kelvin. Okay, so those are our 5 that we'll use in here. All right, so number 2, it says, what is the symbol and meaning for each prefix? So this is where you'll need your prefix chart. So milli, the symbol is just an M, like millimeter, milligram. And the meaning, if you look at your SI prefixes chart, is 10 to the negative 3. Nano, the symbol is N. is D, the meaning is 10 to the negative 1, and centi, the symbol is C, and the meaning is 10 to the negative 2. So again, I just pulled all of that information from your SI prefixes chart. All right, so moving on. List the following units in order from largest to smallest. So on your SI prefixes sheet, the largest units are at the top. You work your way down to the smallest. So let's look. We have milli, centi, micro, which looks like this weird U. It's a mu symbol. Liters, and deci. So if you look, liters is your base unit. It's actually above all of the other ones listed. So liters is actually the largest. If you look right under your base unit, you will see deci. If you look under deci, you will see centi. If you look under centi, you will see milli. And if you look under milli, you will see micro. All right, so that's the order from largest to smallest. So number 4, it says, what's the volume of a paperback book 21 centimeters tall, 12 centimeters wide, and 3.5 centimeters thick? So this one, it doesn't specify anything about significant figures. Y'all, in here, if I don't ask for the correct amount of significant figures, you can just give me the answer. Okay, so we know volume is length times width times height, so I just multiply my 3 numbers. So we have 21 centimeters, we have 12 centimeters, and we have 3.5 centimeters. So I multiply those 3 numbers and I get 882. Now I am picky about this part because centimeters times centimeters times centimeters is centimeters cubed. Okay, so make sure you're cubing that. Alright, so far, not that bad, so let's move on to the rest. We're almost done. Well, with this section. Alright, so state the difference between weight and mass. Okay, so again, this is a verbal answer, so I'm just going to say it. Weight is the measure of the force of gravity on our mass or on an object. Mass is the amount of matter an object contains. So weight is based on gravity, mass is not. Okay, weight is based on gravity, mass is not. So number 2, it says number 6. It says convert 170 Celsius to Kelvin. So we know Kelvin is Celsius plus 273. So it would be 170 plus 273. And of course, when you put that in the calculator or do mental math, whichever one you prefer, you get 443 Kelvin. No degree sign. All right, and then last one, it says state the relationship between joules and calories. So I gave you that conversion factor at the very end of this section, and it is 1 calorie equals 4.184 joules. All right, before you move on to the section 3 lesson videos, please, please, please make sure you understand how to use that SI prefixes sheet because that will make section 3 a lot easier.